Hello friends, in this video today we're going to discuss about particle in 3D box. So for better understanding, so please watch the video made on particle in 1D box, and link of that video is given in the description box. So please watch that first. So let us start. Suppose we have a 3D box as shown in this diagram, such that the distance between the boundaries along x-axis is suppose a, and distance between the boundaries along y-axis it is suppose b, and along z-axis it is suppose c. We have considered that way. And outside the box the potential is infinity, inside the box it is 0. We have assumed that way, that potential inside the box x, y, z, it is 0 inside the box. And potential outside the box, it is infinity. Outside the box, okay, potential is infinity. So therefore particle inside the box, for a particle inside the box, the Schrodinger equation, time independent Schrodinger equation in 1D, we have got that equation this way. Schrodinger time independent equation h minus h cut square by twice m, second order derivative of psi with respect to x is equal to e psi. We have got this one. Actually there should be one more term on left hand side, that is plus v. Here v will be 0 because potential within the box is 0, that's why this term is vanished here. So we have got this equation. But in 3D Schrodinger equation, which is time independent, is given by h cut square by twice m. That's gonna be second order derivative of psi with respect to x plus second order derivative of psi with respect to y, and that of psi with respect to z is equal to e psi, which can be simplified as second order derivative of psi with respect to x, and that of psi with respect to y, and that of psi with respect to z is equal to, you can simplify this one as plus twice m by h cut square e psi is equal to 0. You can simplify this way. Okay, so now here you can see, let us assume that psi, which is a function of x, y, z, it can be expressed as a product of three functions, suppose psi 1, psi 2, and psi 3, and which are functions of x, y, and z respectively. Okay, that means they are each of them function of one variable only. So we can express this. Suppose this is equation number 1 and this is 2. If you use 2 in 1, if you substitute this psi by this value of psi, then what will happen? Here we have partial derivative, so that's why we will consider these two as constant. Okay, when you put here, and when you put here, when you will differentiate with respect to y partially, then we will take y as variable and other two terms as constant. Okay, so hope you know that thing, the partial derivative. Now here you see, so if you use 2 in 1, using 2 in 1, so what you will get? You will get psi 2, psi 3, those were functions of y and z, so that's why psi 2 and psi 3, and then we will have second order derivative of psi 1, so with respect to x. Okay, so here we are not going to use partial derivative because here you see this is function of x, and we have written these two outside the operator, okay, which were regarded as constant. So similarly next term will be psi 1 psi 3, and second order derivative of psi 2 with respect to y, and next term will be psi 1 and psi 2, then second order derivative of psi 3 with respect to z. So hope you have understood this, plus twice m e by h cut square psi 1 psi 2 psi 3 is equal to 0. So that's what we have got. This is suppose equation number 3. Okay, so now you see if you divide this equation by dividing suppose dividing equation number 3 by psi 1 psi 2 and psi 3, then what you gonna have? Then you will have this equation 3 implies, so psi 1 psi 2 and psi 3. If you divide this equation by this term, then it implies 1 by psi 1 second order derivative of psi 1 with respect to x. Similarly we will get 1 by psi 2 similarly 1 by psi 3 plus twice m e by h cut square is equal to 0. That's what you will get. Okay, this is suppose equation number 4. So let us assume this is equation number 4. So now now here you see this energy E, this energy E in 3D, it can be expressed as a sum of its three components. E is equal to, we can express this one as Ex plus Ey plus Ez. We can express in that way, and if you use this here in equation number 4, then you will get this kind of equation: 1 by psi 1 second order derivative of psi 1 with respect to x, then plus twice m ex by h cut square, then plus 1 by psi 2 second order derivative of psi 2 with respect to y, plus twice m ey by h cut square, then plus 1 by psi 3 second order derivative of psi 3 with respect to z, plus twice m ez by h cut square is equal to 0. That's what we will get. Okay, so this equation gives three independent equations. Okay, this equation gives three independent equations, and what are those? So we can write here you see these three, sum of these three can be 0 only if they are individually equal to 0. Okay, if they are individually equal to 0. So that means we can write this one is equal to 0, this one is equal to 0, and this one is equal to 0. So hope you have understood this. So that's why we will get psi 1 this second order derivative of psi 1 with respect to x square plus twice m ex by h cut square is equal to 0. Similarly we will get this one is also equal to 0, and it is also equal to 0. So if you simplify this equation, it will give second order derivative of psi 1 with respect to x plus twice m ex by h cut square, so into psi 1 is equal to 0. So similarly we will get second order derivative of psi 2 with respect to y, not x, y, plus twice m e y by a cut square into psi 2 is equal to 0, and this is the last equation that we will get, plus twice m e z by a cut square psi 3, that's equal to 0. So we will get these three equations, okay. So we're gonna have these three equations, okay. So now you see, this is suppose equation number 5, and this is equation number suppose 6, and this is 7, okay. So now you see, for equation number 5, if you apply the in equation number 1, sorry, not 1, 5, if you apply the boundary conditions, so that psi 1 0 is equal to psi 1 a is equal to 0, because along x-axis we have considered that distance between the boundaries is a, okay, and inside the box potential is 0, outside the box infinity, we have considered that way. So if we apply the boundary conditions in 1D box, we have already got that energy E is equal to pi square a cut square by twice m a square into n square, that we have already got this. So here along x-axis, as we are considering 3D condition, so along x-axis we will get the x component, we will get x ex is equal to pi square a cut square by twice m a square into nx square, that's what we will get. So similarly, applying the boundary conditions in equation number 5, 6 and 7, we have done in 5, and here you see in 1D we also have got the normalized wave function as this psi is equal to psi of x is equal to, we have got root 2 by a. So that's why I asked you to watch the video which is made on 1D box, that will help you to better understand. So we have got that normalized wave function in 1D box, that psi of x is root over 2 by a sine n pi x by a, that's what we have got. So here psi 1 x will be equal to root over 2 by a sine nx pi x by a, that's what we will get. So similarly, applying boundary conditions in 6 and 7, okay. So if you apply boundary conditions in 6 and 7, so what are the boundary conditions for 6 and 7 along y and z axis? Psi 2 is equal to 0, psi 2 0, and psi 2 at x is equal to b. So here in y axis we have considered distance between these two boundaries is b, so then this one 0, this one as b, we have considered that way. So at x is equal to b, here it will be 0, and similarly psi 3 at x is equal to 0, and psi 3 at x is equal to c is equal to 0. So therefore, so corresponding energies will be given by ex, sorry, not ex, ey is equal to pi square a cut square by twice m b square into ny square, that's what we will get. And the z component will be ez pi square a cut square by twice m c square into n z square, and the normalized wave functions will be z2 y root over 2 by b sine n y pi into y by b, that's what we will get. And psi 3 will be equal to root 2 by c, then sine nz pi z by c into nz square. That's what we will get. Okay, so that's why if you add the three components of energy, then you will get the total energy E. That's going to be equal to E is equal to, we know, Ex plus Ey plus Ez. So if you add these three, this Ex, Ey and Ez, then what you will get, adding these three, you will get pi h cut square, sorry, pi square, not only pi square h cut square by twice m, and within bracket you will get nx square by a square plus n y square by b square plus nz square by c square. That's what you will get. So this is our energy. Okay, and you would say the total normalized wave function, and the total normalized wave function, which is given by psi x y z, function of x y z, which is nothing but product of x1 psi 1 psi 2 function of y and psi 3, which is function of z, product of these three, isn't it? So if you put these three values, psi 1, here you see, let me use another ink here. Okay, if you use this psi 1, values of psi 1, psi 2 and psi 3 here in this equation, if you put those, then what you will get, you will get the total normalized wave function. That's going to be equal to root over 8 by abc, root over abc sine nx pi x by a dot sine ny pi y by b and sine nz pi z by c. That's what we will get, psi, total psi normalized function, total normalized function, which is a function of x y z, is given by this. So hope you have understood this. That is what we have got now. Now one more thing, if suppose a is equal to b is equal to c is equal to l, that means all the three dimensions are equal, then this expression E will become, if you put here L square instead of A square, L square instead of B square, L square instead of C square, then what you will get, then E will be equal to pi square by h cut square, pi square into h cut square divided by 2m, L square can be taken common, then here you will get nx square plus ny square plus nz square. That's what you will get. So hope you have understood. So thank you for watching. If you are new to my channel, please subscribe the channel and inspire me to create new contents for you. And if you like this video, hit the thumbs up button and share with your friends.